We're continuing with section 3.1, what differentiability looks like. And remember that f of x is said to be differentiable at x equal to a if the derivative f prime of a exists. Now, if f prime of a exists, then the graph of f is locally linear at x equal to a. That's the basically, this is what we understand from the differentiability. If you really zoom into the graph at x equal to a, if f prime exists, then the graph is going to be linear. As we zoom in and on the point A in f of a, the graph becomes nearly indistinguishable from the tangent line. So here, if you look at this graph, and let's see, if you basically zoom in it more and more, you see that the graph, the orange graph and the blue line become the same. As you just make the box smaller and smaller, the two of them become get closer and closer to each other, and so it's locally almost linear. So what differentiability looks like again? If f prime does not exist, then the graph of f is not locally linear at x equal to a. For example, the function y equal to absolute value of x, remember this one was continuous, is not, but it's not differentiable at x equal to 0. As we zoom in toward 0 and 0, the corner in the graph does not disappear, it just stays. So f is not locally linear at x equal to 0, and we cannot expect f prime to exist. So look, in here, well, we take the little radius 1 around the point 0 and 0, and then we take smaller and smaller, and still it's completely that V shape and it doesn't disappear. So example 3, points of non-differentiability. What do they look like? So we know that one type of the non-differentiability is discontinuities. You can quite tell in here when the function is discontinuous, like this one, f of x equal to x over absolute value of x. By the way, this has another definition. That is using piecewise defined function, because there is absolute value in there. So at point 0, even if we put a point value for it, we will not get a differentiability in there because there's a discontinuity. At corners, obviously, just now we explained that corners are not differentiable. So g of x equal to absolute value of x, or this funky function that you will graph eventually in this course, x to power 2/3 times 6 minus x to power 1/3 has a point that is not differentiable at x equal to 0. And then vertical tangent lines don't count, because we're saying that if the limit is infinity and derivative is a limit, we say that the limit doesn't exist. So vertical tangent line is not, also are places that the derivative doesn't exist. And so this example is out of x, third root of x, and there's a vertical tangent line. And then there's oscillating secant lines. And so this is an example that we already discussed a little bit. F of x equal to sine of x sine of 1 over x if x is not equal to 0, or 0 if x is equal to 0. And so if I go to this applet, you will see that the secant line basically oscillates too much and remember, sine of 1 over x itself oscillated too much to have a limit, then x sine of 1 over x oscillates, its secant lines oscillates too much for it to have a derivative. And so that's the and then I think the x squared sine of 1 over x is where if you replace this part by x squared sine of 1 over x, is where you're getting at a point that you can actually find something that has derivative. So if you go to the app, you see that right now this point C is getting closer and closer to A, and as it gets closer and closer to A, the secant line just goes crazy and oscillates really, really fast. To actually be able to fix this, you can move it on to this point. When you have a g of x squared sine of 1 over x for x not 0 and 0, when x is 0, you see the oscillation, and now it's going that way, it's coming back, and so the oscillation calms down as the secant line, the other point on the secant line, gets closer and closer to the point 0 and 0, and so we started with without any x multiplying, it wasn't even continuous. With x multiplying, it was continuous, not differentiable. This one was continuous, not differentiable. And when it's multiplied by x squared, it's both, it's differentiable and continuous. And we discussed how differentiability and continuity are related. So we're ready to make a huge statement, and this is a very important one. If f of x is differentiable at x equal to a, then f of x is continuous at x equal to a. Warning, it's very important warning. Continuity does not imply differentiability. So one way, if it's differentiable, it's going to be continuous, but if it's continuous, it doesn't have to be differentiable. It could or it could not. Either way would work. And so now I like to do a quick proof of this statement that we made. So if f of x is differentiable at x equal to a, then the limit as x approaches a of f of x minus f of a over x minus a exists by the limit definition of the derivative. Now, limit as x approaches a of x minus a is equal to 0, right? Because you just plug in this part, you just plug in, and that's the direct substitution. And so if this is true, by product law, you can multiply this and that limit, and then when you multiply them together, it would be the limit of both of them exist, so it would be the limit of the product. What is the product of this and that? It's just the f of x minus f of a. So that means that limit of f of x minus f of a is equal to this limit times this limit. That limit existed, and there's a number for it. You multiply it by 0 and you get a 0. So the limit of f of x minus f of a equal to 0. Now use another limit property. That's the property of sum and differences. And so limit as x approaches a of f of a, it is going to be equal to itself. So this limit, when you use that sum and difference of the limit law, then you will have limit of the first one minus limit of the constant. Minus limit of the constant, but limit of the constant is constant itself, and that's f of a. Now subtract minus f of a from both sides, or add f of a to both sides, and you get limits of f of x as x approaches a is equal to f of a. And that was the proof. You just started with this limit existing to this limit existing, and that was the proof of it. Again, I want to emphasize if f is differentiable at x equal to a, then f is continuous at x equal to a. And continuity does not imply differentiability. So if f is continuous, it may or may not be differentiable. Now let's give some examples. And so example, this function g of x equal to absolute value of x is continuous everywhere, but it's not differentiable at 0, 0, right there. This function h of x equal to x to power 2/3 times 6 minus x to power 1/3 is continuous everywhere, but it's not differentiable at x equal to 0. And so white noise is and so does white noise. White noise has a lot of sharp edges, and you have to put filters in them to. Example 4. Each limit represents a derivative f prime of a. What is f of x and what is a? So let's see. F prime of a, if it exists, is going to be equal to, one of the formulas is this one, f of a plus h minus f of a over h. Okay. And this seems to fit well with that formula. What you want to notice is that when you're subtracting f of a. See if it works. Can this be f of a? And I'm sort of, because I have a 5 to power 2 plus h, I see that not a bad idea to write 25 as 5 to power 2. So that makes over here also, so it makes basically f of 2 equal to 5 to power 2 maybe, and f of x to be 5 to power x. Does this fit the first one? Does that make the first one f of 2 plus h, basically? The first one is 5 to power 2 plus h, so it would work. So just messing about with these things, you figure out, oh, f of x should be 5 to power x and a should be 2. Now the question is, how do we find this limit? We will have a little bit more discussion about this specific limit, but let's remember this. First, it's 5 to power 2 plus h, so it's 5 to power 2 times 5 to power h minus 5 to power 2 divided by h. Clean this up to be 5 to power 2, which is 25, times 5 to power h minus 1 divided by h. 25 comes in front of the limit, and the purpose is, for now, we want to learn that this limit is going to be equal to, so soon enough we will learn that this is going to be equal to natural log of 5. So the entire thing becomes 25 natural log of 5. And we're going to have more discussion about this in later sections. Now, what about this limit, part 2? Limit as x approaches 1/4 of 1x minus 4 divided by x minus 4. If looking at this, the denominator looks like x minus 1/4, so I think this formula is used. x to power a of f of x minus f of a over x minus a. So x minus a and x approaching a means a is equal to 1/4. Then and the numerator, I see that f of x should be 1 over x. Does that fit f of a? Yes, then f of 4 is going to be 1 over 1 over 4, which is 4. So this is working. My question is, how do I find that limit? Okay. So let's try to find this limit. How do I do that? It's let's see, we need to simplify this, right? And every case of if the derivative exists, the limit definition always is 0 over 0. So in here, you want to simplify for sure. So in here, I'm going to go limits as x approaches 1/4 and 4 minus. It would be 4 minus. It would be not. It would be with a common denominator would be 1 minus 4x divided by x over 4x minus 1 divided by 4. And so the numerator and denominator have 4x minus 1, which simplifies and becomes a -1. See, this one is the opposite sign of that one. So it's limit as x approaches 1/4 of -1 over x over 1/4. This is limits as x approaches 1/4 of -4 over x, and x approaching 1/4, it gives you -16. The last part of example 4, how do I find this limit? Again, this one I think is limit as h goes to 0 of f of x plus h minus f, or f of a plus h, sorry, minus f of a over h. And so in here I see that this one is basically 5 to the power 3, and I see that power 3, that's why I assume, and this one is 5 plus h to power 3, right? So it seems like f of x should be x to power 3, and that makes a to be 5. And so now, how do I find this limit? Again, every time if the derivative exists, the limit definition of derivative is the form 0 over 0. So you have to follow the knowledge that you have for the limits of the form 0 over 0. And so this one becomes limits h goes to 0. Again, I know that h equal to 0, and h over here is the factor that makes the denominator 0, and it should be the factor in this case because it's a polynomial on top that makes the numerator 0. Two ways of doing this: either expand 5 plus h to power 3, or use this formula, a to power 3 minus b to power 3 is equal to a minus b times a squared plus ab plus b squared. And if I use that, I get 5 plus h minus 5. A is 5 plus h here, and b is 5, and then times 5 plus h to power 2 plus 5 times 5 plus h plus 5 to power 2 divided by h. Now you see that this is actually h, so you can simplify it with that one, and you end up with limit as h goes to 0 of 5 plus h to power 2 plus 5 times 5 plus h plus 25. And this one is not an indeterminate form, so you can plug in and do the direct substitution, and what you get is 5 to power 2 plus 5 to power 2 plus 5 to power 2, which is 3 times 5 to power 2, 75 is